I recently came across an interesting set of data that's published by the Factory of the Future from Bosch Rexroth and is described in this paper by Mohammed Ali Tani and his co-researchers. In this case, the goal was to determine the quality of a CNC machined part based on vibration data. So the machining center was instrumented with vibration sensors, and many values were recorded while the machining center was running to determine good and bad jobs. As you might expect, what you end up with is this is typical style vibration data. The real challenge is that when you look at this in the time domain, you really don't see very much. And so the secret is to move from the time domain to the frequency domain. So perform a Fourier transform on the data. And then you will see clear spikes at points where there is a particular prominent frequency in the vibration data. Now, I took this data and started to analyze it in MI Studio. MI Studio, if you don't know us from semiconductor, MI Studio is a very powerful drag and drop low code no code tool that lets you build applications by linking components together. Much more than something like Node-RED or similar, it's actually a complete contextual AI platform where you're actually building a model of what's happening within the environment. In this case, we actually have a fairly simple application. What we have is this feature extractor, which is going to do all the work for us. This is going to pull the data. We've stored the data into a database. We've imported the data into a database. This is going to search the database for the appropriate data, and it's going to do the analysis we told it to do on that data. I worked fairly closely with a large language model to develop the configuration for this. This is actually configured with a JSON script. And the final result seems quite interesting from the standpoint of a single analysis approach seems to work for a lot of this different data. So this block will perform the feature analysis. It will generate the output from this. It can work with any time series data. So it'll also put out the sample data. In this case, we've got a spectrum coming out of this, the frequency side of the equation. But it also puts out analytical values, and so we can compare one run to another. This in semiconductors is called run to run. Here we're going to compare good runs and bad runs analytically as well as graphically. It has excellent visualization capabilities, and visualization in this case is really not just about decorations. It's really about being able to see what's going on in the application and see what's going on in the data and uncovering values that may otherwise be hidden in your data set. Once you build an application in MI Studio, you can decide where you're going to deploy it. You can deploy it to the cloud, you can deploy it to an edge device, you can deploy it to any kind of IoT system. Since this data was delivered by Bosch Rexroth, I figured the most appropriate platform to deploy it to was a Bosch Rexroth platform, the Control-X platform. And this is an X3 processor from Control-X. And so you see that we have our snap running down here that supports MI Studio. And from that, we can get views into the application. So here's a quick description of what we're expecting here. We've instrumented our machining center with sensors. As anything starts to move, you could reasonably expect it to create some vibrations that are detected by the sensors, and that's what we're going to do the analysis on. So we look at this. This is machine 1, operation 5, which is a step drill running at 200 hertz. And we see here a huge peak at 200 hertz, which is the RPM of the run. So the spindle is running at 200 RPM. And you'd kind of expect to see a spike there. The interesting thing, though, is that the data from Bosch Rexroth was labeled as good and bad. So we know which runs are good and which runs are bad. And it turns out that's a bad run. And if you remove the bad run from the image, you suddenly see that there is no longer any significant peak at 200 hertz. And we see across pretty much this whole data set that at the RPM, at the frequency of the cutting tool, we only see huge peaks, and this is a log scale, so this is a hugely more powerful peak than the um, than a normal run. And this, I don't claim to have done all the research on this, but it's an interesting thing to follow up on, because if this holds across the whole data set, and it seems to hold across just about every value I've looked at, rather than trying to use a black box AI/ML model that needs training, now you have a very fast, pure analytics system where you can determine whether a lot is good or bad. And you can determine it very quickly. Within the first 4 seconds or so of running this lot, you can see whether the lot is going to be good or bad. There are some interesting artifacts on that. I want to start this processing on the machine 3 operation 10 lot, because as much as I like deploying it to this platform, the X3 is not a speed demon, and I want to show you that lot, but it's 40,000 samples and it takes a little bit to run. But we start to see some artifacts here, and one of the most interesting artifacts is that there's a 250 hertz line here. It turns out that a great many other operations within this environment are running at 250 hertz. So then you start to wonder, when you see a frequency band at 250, was there the possibility, and we see the harmonic of that, so it's not just it's a real band. Was there the possibility that some of these runs were actually run not at the correct speed of 200 RPM, but actually will run at 250 RPM? And so that points out a shortcoming of the data. The vibration data is not necessarily sufficient data set to determine the answer to this question. What we really need to know is the speed of the drive. Was this really running at 200 hertz, or was this really running at 250 hertz? And that becomes very important in the next set that I'll show you, because this set, in fact, although it looks as though it was a successful set, it looks as though this is again a step drill. We'll see it in just a second. This is in fact a step drill, and it's running at 250 RPM. And what we'll see here is that the run that shows up with the most power at 250 RPM is actually not a bad run. This is a run that was actually good. So we can consider this run a failure for our theory, which is that the highest energy run, the high energy runs at the machining speed are generally bad runs. However, when you look at this data more closely, you see that there's a peak at 165, 164, and again a harmonic at 300 and something, which again suggests that in fact the RPM of this tool was not always 250. That either for part of the run or for entire runs, this step drill was actually run at a different speed. It was not consistently run at 250. And if we take out all the runs, if we take out this is a single bad run. If we take a look at the single bad run, we see that this has an extreme peak at what we can reasonably speculate was the actual rotation speed of this operation. So to verify this and to complete this research and to know whether this is a viable way to find out in a matter of a few seconds whether the run is good or bad, we need another piece of data. We need to pull the encoder speed into this. One of the nice things about the Control-X platform is that with MI Studio and Control-X, you could in fact do all this in one place. We could collect all that vibration data, we could collect the encoder speed, and be running all that within this single application. Normally you wouldn't have 40,000 runs for a single run, you have much less data. And so this platform becomes a great target for this. You can collect the data, you can analyze the data, and you can decide whether the run is good or bad in a very efficient way. And to do that, what you need is not the graphs are great. They show humans great things, but what you need is some hard numbers. And of course, at the same time as the graphs are calculated, we also calculate the hard numbers and the comparison with run to run. And so these are the numbers that can be used to create concrete analytics, robust analytics for this solution. As I say, this was entirely created in MI Studio. There's a definite low-code operation going on here, and it turns out that really we just need one style of um, analysis to perform all this analysis. And so if you look at the flow here, this is the operation we're choosing. The analysis is performed on whatever was selected in the combo box, and the chart and the table analysis are output. Had it not turned out that way, had it turned out that in fact we needed a bunch of different request JSONs, we have some more tools to apply to this. Within MI Studio, we do have an LLM prompt tool, and either human-generated prompts or machine-generated prompts can be used to populate this tool condition. They can be used to say what should the configuration of this analysis be. That's a much more powerful solution than asking an AI, a large language model, to think across time series data. We're not asking it to analyze time series data. We're asking it to produce a set of rules that it would like to see run across that time series data. And then when that data comes back in the form of solid, manageable data, it can then make decisions based on that information. Adding to that again, we also have a knowledge base. And what a knowledge base does, it'll rag and code documents of all kinds. So if necessary to enhance the time series analysis, you can add manuals, maintenance records, any kind of information. It'll encode images, so you can have documents with images in them that'll tell you what happened with that tool, what went on with that tool. You can construct work orders. It's a very powerful tool beyond just time series analysis. And so that's MI Studio. MI Studio lets you do this kind of time series analysis very quickly. It lets you get real values out of it. It lets you visualize those values, and it lets you build applications that have the analytics you need.